I will introduce you in this presentation. I will talk a bit about phase change materials, and then show you how we are trying to use energy storage in a simple method, and then I will show you a couple of equations, test results, and implementation of our product. Right, so this was the summary. So most of the phase change material application, I think, it's using the latent heat of the material. And if we take a simple case of the ice, if you drop an ice cube in a water, then you would expect that the water temperature would drop. And depending how much ice you put in the water, then this drop would be more or less significant. So the analytics behind this is simply you multiply the latent heat of the ice with the mass of the ice, and then you get the energy you are taking out from the water. And for the water, you are simply multiply the heat capacity of the water with the mass and the temperature difference. Right? So in each case, you are arriving to about 42 kilojoules. Now, in terms of buildings, we have to use this range of melting and solidification, but obviously it's not good to be around 0 degrees. And that's why PCM materials are focusing to have their phase change around 20-25 degrees. Of course, if we have around 20 degrees, we have a better cooling effect, but then we are running into a problem at nighttime because we need to solidify the PCM. So basically, we are interested in salt hydrates and organic, which are based on some fatty paraffin oils and plant oils. So this can be any plant-based oil. Right, each of these materials have their advantage and disadvantage. The salt-based materials are a bit heavy, and in time they tend to separate into components, but they are cheap and environmental friendly. The organics have higher energy density, but a bit more expensive and also a bit flammable. However, they can make it can be made not to be flammable if we mix with flame retardants. So, if you are just looking at the energy content of the PCM materials, we can see that we can substitute quite a large amount of traditional building materials with them. So is it that easy to go from a traditional building into a modern building? Well, anyway, the PCM gives us the freedom to design new building while we are still keeping the mass of the building, right? Okay, so there are a couple of passive building materials which we can use indoors. Yeah, this can be wall boards, ceiling panels, can be even incorporated into glass. So, which in that case, it's very useful for sunshine to absorb the energy from the sun. However, we need to remember that with natural convection, especially when we are just using indoor materials, the natural convection is a bit limiting the heat transfer into the materials, from the air into the materials, and the other way back. So there are a couple of factors which are influencing this heat transfer. Well, the heat transfer coefficient is fairly low. Then we have limited area available in a space, especially if we have furniture and other things. The temperature difference between the wall surface and the air is also not so great. Just a couple, we can talk about a couple of degrees. And all of the heat transfer process has to be done in about 6 hours maybe, anyway during nighttime and during daytime. So at nighttime we would need to freeze the material, and at daytime we would like to melt the materials to take away heat from the room. And then we don't have any control over this heat transfer process. We can't deliver the heat when we want and where we want. So that's why at Monodraught we are trying to combine this heat storage capacity with some active methods to increase the heat transfer, and also we would like to improve the energy, the control strategy, and to deliver the heat when we want. And for this we don't need too much, just an efficient air handling unit, a storage. In this case I would call this a thermal battery, and we would need to be able to bypass the thermal battery or to deliver the ventilation air directly to the space. So this is what you can see here. We have external air coming into the air handling unit. Then we can choose whether to deliver directly if the outside air is cool enough. And alternatively, we can use the PCM battery to cool the air, especially yes, if over night time this PCM was frozen. The heat exchanger itself is basically a parallel plate heat exchanger, and what we have here, flat panels filled with PCM material. This is commercially available, so we are just using this stack, and we have forced convection through this heat exchanger. Okay, we were trying to improve this. This module was used in 2011-12, and then we were trying to improve this model to reduce the noise level, to improve the air distribution, and to reduce the fan powers. So that's how we arrived to our current module, which you can see here. We separated the recirculation module. Previously it was at the side of the air handling unit. Okay, now we can move away from the central unit. This way we can have a better air distribution in the space. And we modified the air handling unit in a way that we have a central rotating part which would divide, in one case, the air to the PCM, or in the other case, as you can see, there are 4 channels inside. And if we want to deliver the air directly to the space, we can use these channels. And this is also a kind of sound detonation. So the whole system would operate quietly. This is very important, especially if we have a classroom. The noise requirements are really tight, and we need to hit 35 dBA noise requirement. So we couldn't do it with the previous model, but with this model, we are really at the edge of this requirement. Okay, the system can be installed either exposed or above the ceiling. And just a short overview about the performance. We can deliver up to 260 liters, nighttime a bit more. And fan power is really down to about 7 watts for the new unit. And thermal energy storage, we made it a bit flexible. Now we can have a bigger or smaller unit in a room. Operation principle is really simple. If this graph shows CIBSE admittance modeling, if you don't have cool phase, that would be the expected temperature in a classroom. And now what cool phase does during nighttime, it tries to freeze the PCM, so we are emitting a bit of heat, and which is expelled during nighttime. And at daytime, we are melting the PCM, so we are taking away heat from the room, and in that way, the peak temperature in the room will be less. Okay, well, we did a fair bit of testing and modeling. First of all, we had to make sure that our air handling unit is operating as we expect. So we're not just using an efficient fan, but the envelope of the fan has to be also efficient, so to get at the least loss. Then we were carrying out testing, CFD calculation, and analytical calculation. Now, for the analytical calculation, what we are using is the heat transfer process on the surface of the panel and the heat transfer for the fluid. So the fluid gets into the heat exchanger at 1 degree, and then it comes out at another degree. And as you see, this modeling show a fairly good agreement. Now, the first data what we received from the manufacturer is the enthalpy diagram of the PCM material. And the above the line with red is for melting, and the blue one is for solidification. So as you see, it's not like with water we have a single degree of melting and solidification. In case of phase change, we have a bit of shift. And if we want to use this capacity, we really need to cool down the PCM to the end of the solidification process, so to about 18 degrees. And when we are melting, it's completely melted at 25 degrees. Right, so if we multiply this, this graph was for 1 gram of material, and if we want to work with 100 kilogram that one thermal battery contains, that this is the thermal capacity we can expect from the system, which is about 4 kilowatt hours. The same we should gain back at night time when we are freezing the PCM. Then we are getting away about 4 kilowatt hours. Right. Now, in comparison with concrete, in green you can see the concrete characteristics, or in cumulative figure, if you are looking at 14, 15 degree temperature difference, we need about 12 kilogram concrete to match the thermal capacity of 1 kilogram PCM. Now, because if you want to hit 10 kilowatt hour, then we would use, well, our system is using 200 kilogram of PCM, and the concrete would be about 2.4 tons. Yeah. This is our test rig. We can control the flow rate, temperature. We are exposing and to an even temperature the PCM. At night time or before the measurement, we are getting an even steady state level, and then we are exposing the PCM to a high level, and then we are measuring the temperature before, after, surface temperature. We know the flow rate, and from here we can calculate heat transfer coefficient and other parameters. Similar measurement with the new unit. In this case, I am testing here a single module of the new unit, so we can use 2 modules, 3 modules, or even 4 modules on one side, and the same on the other side. So if you see the temperature here, exposing, starting at 15 degree, ending at 28 degree, the energy what we are getting out, that's the blue line, that's the cooling power, so it's almost a bit less than 4 kilowatt hours. At night time, when we shut down the system, we are trying to come back to 15 degrees. Then this is the heat released from the PCM, and again we are ending up at around 4 kilowatt hours. The same graph just carried out for the one module of the new system. Right, so we made a modeling based on the equation I presented before. If we translate this into in time, then we can really predict if we are exposing this battery to a temperature profile, what can we expect, what is the outcoming temperature, and what is the profile of the thermal power. This is the thermal power. You can read it here. It's giving about 400, 500 watts. And in the blue line, you can read that's the accumulated energy we are getting out. Right. During this time, so nighttime charging, we are consuming, this is for the old system, we are consuming some electric power over the charging period, and we are getting rid of the thermal power and thermal energy. And at nighttime, at daytime, we are melting up the PCM, and we are gaining this sort of thermal energy, and the thermal power is again, it's terms of cooling now, it's around 500. Okay, now we know the thermal energy, and we know how much energy we consume, and then if we simply divide them, we can get the energy efficiency ratio of the system, which is, those who are familiar in this topic, it's fairly high. For the new system, this figure would be even higher because we consume less energy with the smaller fan. This graph shows how the modeling compares with the measurement. I can say that though it's a simple model, we could get a really good agreement between the test results and the modeling. And now we know how our system is behaving. We would like to model how it behaves over in a room over a season. So for this, we would need to do dynamic thermal modeling. But at that time, when we developed the system, none of the software vendors were handling phase change materials. So we were kind of stuck, how are we dealing with this? So we have weather data, and what we did, we categorized each day being in a certain temperature range. And for each temperature range, for each category, we created a 24-hour pattern. So we know we would expose our system to this pattern on a warm day, on a cool day. And with the use of our model, we can extract basically a starting power, a thermal power, and the temperature profile. So the profile of how this power is distributed over the melting period. And this is what we can give to the software doing the dynamic thermal simulation. Now, you don't have to do this now because all this work was implemented into the software, and the user what needs to do is simply select our system from a selection panel, and then that's it. The building will operate together with our system. The system is basically it's an HVAC system which is integrated into the building. All operation and set points are predefined, and then you just need to run the simulation. Finally, let's see a bit of case study. Right. This is a case study on the Delta system when we first installed into a classroom in London. It's Notre Dame School. It was an IT classroom with quite a lot of computers. And then we had another classroom for comparison, and another IT classroom, and a normal classroom which was next to our targeted room. So here you can see the outcome. Before installation, the IT classrooms were behaving the same. They had around 25 degrees temperature on average. Then we installed our system and we measured again. The average temperature came down to around 21, 22 degrees. So I would say this is too good. But combined this with a very good ventilation rate, then this is what we could achieve. Looking at carbon dioxide temperature levels, again, before it was based on natural ventilation, so they could just open windows and the cooling was made with the air conditioning unit. Then our system introduced a good ventilation, and also the carbon dioxide levels dropped significantly. All right, so I guess that's all. Thank you very much.